A non-uniformly charged slab. A slab of insulating material has thickness 2d and is oriented so that its faces are parallel to the YZ plane and given by the planes x equals d and x equals minus d. The y and z dimensions of the slab are very large compared to d, so treat them as infinite. The slab has charge density given by rho as a function of x is rho 0, where rho 0 is a positive constant, x divided by d parentheses squared. Using Gauss's law, find the electric field due to the slab, magnitude and direction at all points in space. Alright, so if I draw this slab, it has infinite dimensions on the y-axis and z-axis. It has finite dimensions on the x-axis. It extends all the way to minus d and plus d. If I take this Gaussian surface S1 inside this slab, I see that if this is a cylindrical surface, the electric field lines will be in either plus I hat or minus I hat direction. I have a positive charge distribution inside, and it's going to be parallel to the area vector of this cylinder. So for this Gaussian cylinder S1, I can use Gauss's law. So I noticed that the charge density, rho, varies with x. It's not a uniform charge distribution, and it's given by rho 0 x divided by d parentheses squared. And you can see that this is a function of x squared, which means if I have x replaced by minus x, I would find the same charge distribution. So there is symmetry in the charge distribution on the positive x-axis and negative x-axis. So I note that rho of plus x is equal to rho of minus x. So what does that imply in terms of the electric field? Electric field as a function of x is also equal to E as a function of minus x. So electric field at point x will be equal to the electric field at point minus x because you have exactly the same charge distribution. It's symmetry. So due to symmetry, we have electric field at point x equal to the electric field at point minus x. And furthermore, I noticed that the charge density at x equals to 0 is 0. So if I look at the electric field at x is equal to 0, which is on the YZ plane at x is equal to 0, since I have no charge there, the electric field at x is equal to 0 will be equal to 0, and you can see that these electric field lines are pointing in opposite directions. We start from 0 and the electric field starts increasing as we go farther away on the x-axis because the charge is increasing quadratically with x. All right, so electric field at point x equals to 0 must be equal to 0. Now let's start working on this Gaussian surface S1. For the S1 Gaussian surface, x values are less than absolute value of d, which means it's either less than plus d or smaller than minus d. Okay, so if I write Gauss's law, the closed surface integral electric field dot dA, the net flux through this Gaussian surface is equal to, now since you have this infinite y and z dimensions and positive charge distribution here, electric field lines should be along the x-axis. So this tells me that the electric field lines and the area vector at the cap of this cylinder must be in the same direction, and it must be perpendicular to this area vector. So the only contribution to this closed surface integral comes from the top and bottom surfaces. So I will have E times 2A for the value of the net electric flux, and this must be equal to charge enclosed Q in divided by epsilon 0, permittivity of free space. And what is Q in here? What is the charge enclosed? It is the integral from minus x to plus x, the charge density rho dv, divided by epsilon 0 will give me the net flux. All right, so let's find the charge enclosed. So what is Q in? It is the integral from minus x to plus x, rho 0, x squared divided by d squared. And what is the volume element here? It's the area multiplied by dx. So it's going to be a dx. So since I have the symmetric situation for minus x and plus x, I can write this as twice the integral from 0 to x, rho 0, x squared over d squared, a dx. All right? And this charge enclosed will be equal to, now I can take 2 rho 0 a and d squared outside. So let's rewrite this as 2a rho 0 divided by d squared. I have the integral from 0 to x, x squared dx. The integral of x squared dx is x cubed divided by 3. So this will give me 2a rho 0 divided by 3 d squared, and then I will have x cubed. Now, x cubed is to be evaluated between 0 and x, but that is equal to x cubed. So normally, if I'm using this x here, this should be a dummy variable, x prime, right? So x prime square a dx prime, x prime square a dx prime, x prime square dx prime, and the integral gives me x prime cube. Evaluated at x becomes x cube. All right. And now I can use Gauss' law. E times 2a is equal to 2a rho 0 x cubed divided by 3d squared, but then I have to divide it by epsilon 0. So 3 epsilon 0 d squared, because it is charge enclosed divided by epsilon 0. I can see that these two a's will cancel out, and I will be left with an electric field magnitude for x less than absolute value of d, rho 0 x cubed divided by 3 epsilon 0 d squared. All right. Now we're ready to write the electric field vector for the two regions, x greater than 0 and x less than 0. So the electric field for x between 0 and d is going to be rho 0 x cubed divided by 3 epsilon 0 d squared. And what is the direction here? On the positive x-axis, it's in plus I hat direction. And the electric field for x between minus d and 0 will be equal to the same magnitude, rho 0 x cubed divided by 3 epsilon 0 d square, but this time in minus I hat direction. So we have found the magnitude and direction of the electric field. Now I want to move on to Gaussian surface 2 in order to calculate the electric field outside the slab. Now for x greater than absolute value of d, I need to calculate the charge enclosed, the total charge enclosed. This will be the integral x varying between minus d and plus d, rho dv. This will be the integral x varying between minus d and plus d, rho 0 x prime squared over d squared a dx prime, because I'm using this dummy variable x prime as in the previous case. This will give me rho 0 a divided by 3d squared x prime cube evaluated between minus d and plus d, and that gives me 2a rho 0 divided by 3d square d cube. So for x prime, I substitute d, I obtain d cube, and then I substitute minus d, which gives me minus d cube. D cube minus minus d cube gives me 2d cube. So I obtain 2a rho 0 over 3d squared d cube, and I see that I have a cancellation of d squares here. So this d square will get rid of this cube, make the top d, so that the charge enclosed by this cylindrical surface will be 2a rho 0 divided by 3 multiplied by d. So here I'm considering the Gaussian surface S2. So that's basically this Gaussian surface here. Now I can apply Gauss law. The closed surface integral E dot dA is going to be 2EA, and that is charge enclosed Q in divided by epsilon 0. Once again, these electric field lines will be parallel to the x-axis, perpendicular to the area vector from the side surface of this cylinder. So that dot product gives me 0, but these two dot products will give me E times A, and because the electric field value at this point and this point will be the same, because I have symmetry. E of x is equal to E of minus x. That's due to the symmetry in the charge distribution. And this gives me 2a rho 0 d divided by 3 epsilon 0 for the electric field magnitude. So I see that the electric field magnitude here is, because I have a cancellation of these two a's, this 2a will get rid of this 2 and a here. Rho 0d, for x greater than absolute value of d, I have rho 0d divided by 3 epsilon 0. So that means the electric field for x greater than absolute value of, let's write it this way, for x greater than d on the positive x-axis, it will be equal to rho 0d divided by 3 epsilon 0 in I hat direction, whereas on the negative x-axis, we have to be careful. X less than minus d, now it's supposed to point in minus I hat direction, so it's rho 0 d divided by 3 epsilon 0, now pointing in minus I hat direction. So the answer for the direction changes sign. Okay, so in this example, we have a non-uniformly charged slab. What makes it non-uniform? This charge distribution, quadratic dependence on x. It's a slab of insulating material with thickness 2d, and it's oriented so that its faces are parallel to the YZ plane. So it has a face, it has faces parallel to the YZ plane, and the Y and Z dimensions extend to infinity, whereas the X dimension is in between plus D and minus D. So I have an infinite slab which is infinite in Y and Z, but finite on the x-axis. Our rho zero is a positive constant, and we want to use Gauss law to find the electric field at all points in space. For this purpose, first I note that the charge distribution is symmetric about x equals 0, about the YZ plane, and that gives me that electric field magnitude at point x and minus x should be the same due to the symmetry in the charge distribution. And the charge at x equals 0 is equal to 0, which means the electric field at x equals to 0 should be equal to 0. Now, for x less than absolute value of t, I consider Gaussian surface S1. For x greater than absolute value of t, I consider S2. For both of these surfaces, since the electric field lines should be parallel to the x-axis, and they should have the same value on the top and bottom surfaces of this symmetric cylinder that I have picked here, the closed surface integral E dot dA must be equal to 2E times A. There is no contribution from the side surface. The area vector there is perpendicular to the electric field vector. And according to Gauss law, that is charge enclosed divided by epsilon 0. So my task is to find the charge enclosed by this Gaussian surface. In the first case, it will be the integral from minus x to x rho dV, the charge density multiplied by the volume. It is rho 0 x prime square over d square a dx prime. A multiplied by dx gives me the incremental volume. And due to the symmetry here, this is twice the integral from 0 to x, rho 0 x prime square d square a dx prime. So this is prime. And that integral gives me x prime cube over 3. So this gives me x prime cube over this is the x prime squared. The answer of the integral is x prime cube over 3. Evaluate at x, it becomes x cube. So it's going to be x cube over 3. So 2a rho 0 over 3d square x cube is the charge enclosed. So if I rewrite Gauss law, charge enclosed divided by epsilon 0 is E times 2a. I find the electric field magnitude rho 0 x cube over 3 epsilon 0 d squared. Plus I hat if x is positive, minus I hat if x is negative. For the second Gaussian surface, the total charge enclosed is integral from minus d to plus d rho dv. And for this Gaussian surface, dv is equal to a dx again. So a dx prime, rho 0 x prime square over d square. That integral gives me 2a rho 0 d over 3. And the closed surface integral, the net flux 2EA is equal to this charge divided by epsilon 0. So I find the magnitude rho 0 d divided by 3 epsilon 0. You can see that it's a constant. And it's plus I hat if x is positive. It is minus I hat if x is negative. X is less than minus d.